But yeah, do you want me to continue, or shall we call it a day and then continue tomorrow? I can't quite complete the next chapter, so sometimes starting the next chapter also has its disadvantages. Go ahead and continue. Okay. CH9, please. So we are left with two more chapters. The first one is for interconnected power systems, and the other one is for distribution system reliability. And for distribution system, we'll mostly focus on radial systems, and for interconnected power systems, we'll focus on one particular technique. So let's just sort of introduce this topic today without going into too much detail. So we know by now that we can improve the performance of the system by interconnecting it to another system. I mean, intuitively, we can see that, oh, I have my own system. If I connect it with another system in the hour of need, maybe I can get power from there. Maybe I can get energy from there. And whenever they need, then I can transfer energy to them. I may have mentioned to you on the first day that Singapore has this two submarine cables connected to the Malaysian power system. Malaysia is the neighboring state, neighboring country. But as far as I know, we have not received any power from Malaysia to Singapore, but sometimes we do supply power to the other side. Yeah, it depends on the reliabilities of the system, but it actually is there to assist each other, right? Whenever there is a need. Who knows, tomorrow there might be a need, because all the failures are occurring at random. We hope not, and they are undersea cable or lying on the seabed. I don't know how many of you have been to Singapore and or Malaysia, but there are two causeways that connect Singapore and Malaysia by land, yeah, and there is maybe about 3 to 4 kilometer portion where there is a sea, yeah. So it's lying on that seabed, those two 500 megawatt cables. So the adequacy of the generating capacity can be improved by interconnecting the system to another power system. Intuitively also we can see that each interconnected system can then operate at a given risk level and with a lower reserve, right? So if I have my own system, I have my own reserve, and I connect my system to another one and I take some benefit from there, then my reserve can be lower, isn't it? Because I'm taking some additional capacity, correct? So reserve would be lower, and if there is no interconnection, then of course I have to maintain a certain reserve. It will never be lower than that. So the actual interconnection benefits depend upon some of these factors. The installed capacity in each system. I mean, if my system is 10,000 megawatt, and if the neighboring system is only 100 megawatt, I wouldn't expect a lot of support from the neighboring system, is it not? So the installed capacity is quite a factor. The total tie capacity, now tie means the transmission line or the cable between the two systems. The capacity of that, it's limited, right? The power capacity cannot be, like I said, 500 megawatts in this case. It could be lower, it could be higher. So the tie capacity is another factor. The forced outage rates of the tie lines. All these cables or transmission lines between the two systems, they're going to fail sometime. Even when they're not in operation, they may fail, because sometimes you're just lying there, waiting to fail. And something will happen and you'll fail. So the availability of these tie lines is also a factor. The load levels and their residual uncertainties in each system. So my system is A, the supporting system is B. I have a load level in A, there is a load level in B, right? So these load levels are changing, right? These load levels are not constant. So we need to be aware of the load levels and their uncertainties in each system. So whenever I need power from the neighboring system, maybe they cannot supply because they are on their peak load, yeah? Maybe if they are on their low load, they will be able to supply. So therefore it is dependent upon the peak load in each system. Last but not least, the type of agreement. This is obviously the most important. You have to write down on paper and get it signed by both sides as to when you will support, how much you will support, how much it'll go to, how much is it going to cost, and things like that, right? So the agreement is very, very important, and I'll share with you some of the agreements that usually these interconnected systems have. So there are several probabilistic methods available which provide a quantitative reliability assessment of interconnected system generating facilities. The LOLE approach is the most widely used, so we are going to continue to use that. There are two basic methods in the literature that can calculate the reliabilities of interconnected power systems. The first one is the probability array method, and the second one is equivalent assisting unit method. Now, as you can see the name probability array, so that means that you create a common probability table which represents system A as well as system B, and from that common table you can see how much support B can give to A and how much support A can give to B. Yeah, so that's one method. The second method is equivalent assisting unit method. So we will see how much support system B can provide to system A, for example, and we will then model the support from system B as another generating unit, right? We will model the support from system B as another generating unit, and by now we know how to add a generator to our system, right? So we call that equivalent assisting unit method. The assisting unit is modeled as another equivalent generator, and then we treat this together with our system, and then we redo the calculations and we find how the reliability has improved. Obviously, with assistance, the reliability will improve. In other words, the LOLE will reduce, the LOEE will reduce, correct? That's why reliability is improving, unreliability is going down, right? That's what will happen. So in the first approach, a capacity model is developed for each system, and an array of simultaneous capacity outage probabilities is then obtained from the individual models. I'm going to deal with only the second method. Second approach, the assisting system is modeled as an equivalent assisting unit which can be moved through the tie lines. So I'm going to consider how much support system B is able to provide. I'm going to move that support through the connecting transmission line or cable, yeah, model it as a unit and then add it to my system. Yeah, so it's a very interesting method. The evaluation of the risk in the assisted system proceeds much the same way as in an isolated single system study, which we have been exposed to by now. Okay, so we'll focus only on this approach, equivalent assisting unit method. Obviously, in a more detailed course, we can look at the first method as well, but we can learn about so many methods. The basic idea is we should know how to do these calculations, and I think the second method is easier to do the calculations by hand, so that's the reason I'm focusing on that. We will also study the impacts of some factors. We will vary the tie line capacity, we will vary the tie line parameters, we will vary the peak loads and the type of agreement between the systems, yeah, and we'll see how they can impact the reliability and unreliability of the system. So the equivalent assisting unit approach works like this. It represents the benefits of interconnection between the two systems in terms of an equivalent multi-state unit. It could be a two-state unit, but in general, we expect it to be a multi-state unit, which describes the potential ability of one system to accommodate capacity deficiencies in the other. So we'll process assuming that system A is the assisted system and system B is the assisting system. So I'm in system A, you are in system B, you are assisting me. That's what I'm doing now. We can also do the reverse, obviously. Yeah, but once we know one side, we can always do the other side as well, right? The calculation can be repeated very easily. So the capacity assistance level for a particular outage state in system B, because we are going to be assisted by B, isn't it? So we focus on B first. We say, okay, the capacity assistance is given by the minimum of the tie capacity and available system reserve at that outage state. So for example, if the assistance available in system B is 40 megawatt, but your tie line capacity is only 20 megawatt, obviously you cannot transfer more than 20 megawatt, right? So that's what I mean, that even though the system may be able to transport more energy to my system, but because of the constraint imposed by the timeline, I have to consider that as well, right? So we need to consider the constraints imposed by the tie lines. All capacity assistance levels greater than or equal to the tie capacity are replaced by one assistance level which is equal to the tie capacity. So the maximum level of support will be the level of the tie line capacity. That's what it means. And of course there will be other states, but the maximum will be equal to tie line capacity. Maybe the assisting system B is not even able to provide the tie line capacity. So suppose the tie line capacity is 20 megawatt, but system B says, I cannot give you more than 10 megawatt. So that's okay, then there is no constraint from the tie line itself. But otherwise there can be constraint from the tie line as well. So the capacity assistance table, from system B can then be converted into a capacity model of an equivalent multi-state unit. In general it will be multi-state, maybe two-state for simplicity, but in general it will be multi-state. And then we add this unit to our existing capacity model in system A. So as a principle, as a process, this is what it will be. We'll go to system B, we'll see how much support it's going to provide, we'll see how much it can transport through the transmission line or cable, and then we are going to add that model to our own capacity model and recreate the new capacity model, and then use the load model and calculate the new risk. Okay? So that's the process in simplicity. So let's look at an illustrative example. Assume that the two systems A and B are interconnected by a finite capacity tie line and have the data shown in table 9.1. So system A has 5 units of 10 megawatt each and 1 unit of 25 megawatt. So the total installed capacity is 75 megawatt and the daily peak load is 50 megawatt. Okay? System B has 4 generators 10 megawatt each, 1 generator 20 megawatt. So the installed capacity is 60 and its own peak load is 40. The system peak load for B is 40, system peak load for A is 50. They have their own installed capacities, they have their own peak loads. Clear? The tie line connecting system A to B is one tie line, one transmission line or one cable, and the capacity of that line is 10 megawatt and the forced outage rate of that tie line is 0. For simplicity, I'm assuming that the tie line is 100% reliable. We'll see maybe tomorrow when we change the forced outage rate, how it impacts the assisting unit and how our own system reliability gets affected because of that. So these are the data that we have. This is the way the system is. System A, 75 megawatt load. System B, 60 megawatt load. And it can be connected by tie lines. In this case, only one tie line. Okay. So we know how to calculate the capacity model for each system, isn't it? I mean, these are two individual systems. You can calculate the COPT here. You can calculate the COPT in system A. Probabilities less than 10 to the power minus 8 can be neglected, which we have been saying before. So let's look at this. This is the COPT of system A here and the COPT of system B here. Everybody can do that by now, right? So very simple. And these are small systems, so you can do by hand calculations very easily. Yeah. So the peak load in system A, 50 megawatt. Therefore, the system will fail to meet its own load demand when the capacity on outage is greater than 25, isn't it? The installed capacity is 75, peak load is 50. So whenever we lose more than 25 megawatt, we have loss of load. I mean, we have established that already, right? The definition of loss of load. Capacity on outage may or may not result in loss of load. But if it is more than 25 megawatt, there is definitely a loss of load, correct? So the cumulative probability for a capacity outage of 30 megawatt therefore becomes the LOLE. So what is the risk in system A? The risk in system A is whenever I cannot supply more than 25 megawatt load, right? So if the capacity outage is 30 or more, then this is the cumulative probability, 0.001996767. Are you with me? Cumulative probability tells us that more than 30 or more than 30 megawatt out. This is the cumulative probability, right? And that's my risk in the system, because up to 25 megawatt I don't lose any load, so I don't need to worry. But anything beyond that, I need to worry. This is the risk. Similarly, what's the risk in system B? The system B capacity is 60 megawatt, and the load in system B is, where is that? 40, okay, if you say so. Yeah, peak load is 40. So any outage more than 20 megawatt is going to lead to loss of load in system B. So up to 20 is fine. This state, this is the cumulative probability, 0.00158. So you see that the risk in the two systems is very different, right? Yeah. So system B risk and system A risk. Did I write somewhere? No, I didn't. Yeah, I did. So LOLE index in system A is the cumulative probability for capacity outage of 30 megawatt. Yeah. Similarly, LOLE is the cumulative probability of any capacity outage greater than 20 megawatt. Okay, so we know the numbers there. Now, system B has a reserve of 20 megawatt, correct? Capacity is 60 megawatt, load is 40 megawatt. So its reserve is 20, and this is therefore the maximum assistance it can provide to system A, right? This is the maximum. According to the agreement, maybe the agreement says no more than 10. But so far, I'm not considering any agreements. We just assume that the 20 megawatt is available, okay? So without sharing potential difficulties in system A. The capacity assistance level of system B are obtained from its COPT, yeah? These capacity levels are shown here. So let's go back to system B. System B is going to provide me a maximum of 20 megawatt support, right? So when the system B 60 megawatt is out, cannot provide me any support. 50 out cannot, 40 out cannot, 30 out cannot, 20 out, it's still just able to meet its own load. So it can only provide me support when it is in these two states, correct? So you see here, the assistance from, oops, I think the battery is going down. The assistance probability table from system B, if it can provide me 20 megawatt assistance, what's the probability? 0.9039. Yeah, I think this one is also giving up on me. Yeah, here. So system B, if capacity outage is 0, then the individual probability is 0.9039, right? If the capacity outage is 10, then this is the probability, correct? And when the capacity outage is 20, it will not provide me any assistance because it's able to meet its own load. But it can provide me assistance from these two states, right? So 0.90 plus 0.073, that's the probability, 90 plus 0.073. These are the individual probabilities, right? At this probability, it will give me 20 megawatt assistance. At this probability, it will give me 10 megawatt assistance. And 0 megawatt, the rest of the probabilities, isn't it? That means it is meeting its own load. So this is the equivalent assisting probability table from system B, which I'm now going to move through the transmission line. I'm now going to move this through the transmission line, okay? So what do I do? Equivalent assisting model of unit B. So capacity out 0, I can get 0.9 times. Capacity outage 10, I can get 0.073 probability. And capacity outage 20, the probability is very, very low that it will supply me with any support. So the 10 megawatt tie line connecting the two systems constrains the capacity assistance from system B. I can only transfer 10 megawatt, not 20 megawatt. So how do I now modify this table? I can modify this table, the tie line constrained equivalent assisting unit model of system B now. capacity outage 0 is 0.9039 plus 0.073, isn't it? Because when I'm in this state, I can get 10 megawatt. When I'm in this state, I can get 10 megawatt in my system. So therefore, these two are contributing to the first state. Yeah, and the last one is contributing to capacity outage of 10, because I can either get 0 or I can get 10, isn't it? So after the tie line, the capacity model that is coming from system B is only a 2-state model. But before that, I have a 3-state model. So that's how the transmission line can actually constrain the support from system B to system A. So once I know this, then it's quite easy. This tie line constrained equivalent assisting unit is now added to the existing capacity model. Yeah, we already know our system A COPT. So you can add the new generator. This is like a generator. This is like a generator, a 10 megawatt generator, which has 2 states, right? So, yeah. Ye wala? Yeah. So we have the support from the system B, which is 20 megawatt available or 0 megawatt out, right? I mean, let's go back here. Assistance of 20 megawatt means from system B 0 megawatt out, correct? Assistance of 10 means 10 megawatt out, right? So I'm now writing it in terms of capacity out. And the 3 probabilities are the same, correct? What I'm saying now is that because the capacity of the tie line is only 10 megawatt, we mentioned that earlier, right? The capacity of the tie line is, what did I say? Let me look at it. Oh, somewhere I must have. Is it here? No, previous one. Yeah, here. The tie line capacity is only 10 megawatt. And of course, it doesn't fail, which is not realistic, but doesn't fail, okay? So even though I have a support of up to 20 megawatt, capacity out 0 means I have 20 available, right? But I cannot get 20 because the tie line is constrained to 10. So when it is in this state, I'm getting only 10. When it is in this state, I'm getting only 10. When it is in this state, I'm not getting anything. Correct? So for these 2 states, I'm getting 10 megawatt. Therefore, the probability is this plus this. That means 0.97. And for the last state, the probability is this. So this is like a 2-state equivalent assisting unit after having passed through the tie line. Okay, so now we can generate the new COPT by adding this new generator of 10 megawatt capacity. So previously, if you go back to the system A COPT, this is the COPT. Yeah, the maximum capacity was 75. Now I have another 10 megawatt. So the maximum capacity becomes 85, and you can recalculate the COPT, right? So that's what is given here, the modified COPT of system A, okay? So I have capacity outage states and I have individual probabilities. You see here it has almost become 0. That's why I didn't go further. Obviously there's up to 85, right? Because I've added 10 megawatt, but I don't need to. It's almost already 0, up to 8 digits. It's almost 0 already, okay? So probability, cumulative probability, and then if you know the load, then you can find out the risk. So the daily peak load in system A is 50, and therefore the loss of load occurs whenever the capacity on outage is more than 35. Previously it was more than? Previously when it was isolated, 25, right? Because the peak load was 50, the installed capacity was 75. So cumulative probability of capacity on outage greater than 25 megawatt would give us the risk. Now we have 35 megawatt reserve. So therefore, the loss of load expectation is 0.00012042. Yeah, 0.0001 more than 35. So it is this state. Yeah, 0.00012042. That is the cumulative probability or the loss of load expectation. So has this improved? Has this improved 0.00012004? 0.0001204 as opposed to the previous one, 0.00199. The lower the better, right? The risk, the lower the better. So the system is more reliable, of course. That's what you would expect intuitively. Now we are quantifying the benefits, okay? So this is how the equivalent assisting unit approach works. And we will get the new LOLE, which is given here, okay? Similarly, if we are interested in calculating the LOLE of system B, when we assist from system A, right now I have shown you that the assistance is coming from B to A. Suppose now I ask you to go back as homework and take the assistance from unit A and then transport it through the tie line to system B and find out the improvement in the risk in system B, then you will be able to do that, okay? So you can just repeat the entire procedure. Now there are several factors that affect the what you call assistance from one system to another, and some of these factors we have already alluded to earlier: the tie line capacity, the tie line availability, the agreements between the systems, the peak loads in the two systems, and so on and so forth. So the factors affecting the emergency assistance, we are now going to consider one by one. Do you want me to stop or continue here? Continue? You guys are really driven quite a lot, yeah? So we have now seen that already when we connect the two systems, the reliability improves. We expected that to happen, okay? Now, this assistance depends upon several factors: available capacity and the operating reserve in the other systems, the interconnection limitations, and the type of agreement between systems, right? We can easily appreciate that. The above factors are all interlinked in regard to their impact on the reliability levels. Yeah, so we'll consider them one by one, although they are interlinked. You can also consider them together, but it'll make the analysis more complex. So let's see the individual impacts. We start with the impact of tie line capacity first. So we vary the tie line capacity from 0 to 30 megawatt in steps of 5 megawatt. You remember what was the tie line capacity in the example that we just saw? 10 megawatt. So now I'm saying tie line capacity 0. Obviously no help to system A, correct? If the tie line cannot transmit any power, I'm not getting any assistance from system B. So my original risk, which was 0.00199, stays. And when I have 10 megawatt assistance, this was my new risk, which I saw in the example just now, 0.00012. But what if the tie line capacity is only 5? Then this is the improvement. If it increases to 20, this is the index. Now you see for 25, 30, it is the same. Why? That will tell me whether you are asleep or awake. Why are these two numbers the same? Constrained by the capacity of the assisting system. Assisting system is 60 megawatt, peak load is 40. It will not help me beyond 20 megawatt. So beyond 20 megawatt, nothing will change. You put a 100 megawatt line, tie line capacity, it's not going to matter. It's just a waste, complete waste, okay? So we can do this calculation, and again, you know, if you have the time, please try and do it. A couple of levels, maybe 5 megawatt and maybe 20 megawatt, which is the maximum level of support you can get. So the tie lines considered in the results shown in the previous table, that's this table, 9.7, are considered fully reliable. Remember the tie line forced outage rate was 0? Yeah, I'm assuming that if it is a 5 megawatt line, it's able to transmit 5 megawatt, but normally in practice, that will not be the case. Although you must know that transmission lines are some of the most reliable equipment in power systems. Generators are not as reliable, distribution circuits are not as reliable, but transmission lines are very highly reliable. They are the most reliable components, okay? So it is evident from these results that the risk reduces whenever we increase the interconnection capacity up to the limit that system B can support system A. Beyond that, there will not be any benefit. So the risk converges to a value which represents the minimum risk that system A can have under these conditions. The risk is getting better and better and better, and it will converge to a value that the maximum capacity relates to. The risk at this limit can be designated as the infinite tie capacity risk. Infinite tie capacity risk. That means regardless of how much you increase the capacity of the tie line, it's not going to increase any further, as there will be no further decrease in risk with the addition of further tie capacity. So it's called infinite tie capacity risk. The infinite tie capacity value is directly related to the maximum assistance available from system B, which in our case is 20 megawatt. Yeah? Hence, increasing the tie capacity beyond 20 will have no benefit to system A. So now, let's change the reliability of the tie line. We assumed until now that the tie line was perfectly reliable. Its unavailability was 0 and its availability was 1. Right, so now we change it. So the tie line availability now, we say consider the case in which there is only one tie line of 10 megawatt as before, connecting systems A and B. Assume that the failure and repair rate of the tie line are 3 failures per year and 1 repair per day. Yeah. So what is the availability? Mu over lambda plus mu. Yeah. Mu is 1, lambda is 3. So you can calculate using this. Lambda is given here, 1 repair per day. So it is 365 repairs per year. So you have to use that number and you will get the availability. Okay, so the tie line unavailability is 1 minus availability, which is this particular number. I think we all can calculate that. So now there are 2 states in the COPT for the tie line, which is the same as before, because it is still a 10 megawatt tie line. So I can only transfer 10 megawatt. Remember, we got the 2-state model before, and that's the model from using this availability. The equivalent assisting unit model for a 100% reliable tie line, if we go back here, for a 100% tie line, reliable tie line is this one, right? 100% reliable tie line is this one, correct? No outages in the tie line. But now we have tie line which may not be available. So how do we modify it? So now the new table is this: tie line capacity, nothing is out. The individual tie line 10 megawatt. These numbers. How did we find these numbers? Unavailability and availability of the tie line is known. So if I want to transmit 10 megawatt, the probability when the tie line is fully reliable is known to me, and the probability when the tie line is not available is known to me. So I can multiply those 2 probabilities and I get this individual probability. Similarly, tie line capacity out 10, the probability is 0.0081. So this is my new transmission line constraint model. I can still get only 10 megawatt assistance when the transmission line is up, and therefore the probability of receiving 10 megawatt is 0.9918 times 0.9777, right? You go back to that table. Unfortunately, it's not on the same page. Yeah, 0.9777. Remember this number, 0.9777. So we multiply 0.9777 with the individual probability of the tie line. Yeah. So that's the new probability, correct? So we can do that, and then we come up with this tie line constraint equivalent assisting unit model from system B. We have considered not only the tie line capacity, we have also considered the tie line reliability. Okay? So this is our new constraint model. If you compare with the previous table, the number was 0.9777, remember? Yeah. Now because it is not 100% reliable, you expect this to be lower, correct? So we are on the right path. We have the new model, and of course now you can repeat the calculation and you will get the new risk. What's the new risk? Again, now I look at 40 cumulative probability of 40 or more, so 0.000013572. This is the new risk. 0.000135. 0.000135. What was the risk before? Oops. Here. Point more than 20, right? No, 10 megawatts, so more than 15. 0.000011972. So you can see that the benefit has changed now when the tie line is not fully reliable. Okay. Okay, we have done this. We have done this. Yeah, so this is the new LOLE. Okay. Correct? Okay, we can also do some more sensitivity studies. We can change one tie line to two tie lines and see how much benefit we derive from there. So now we have a case in which the interconnection between A and B consists of two identical tie lines rated 10 megawatt each. Instead of one tie line of 10, now I've got 10 plus 10, 20 megawatt. The failure rate is still the same. Repair rate is 1 repair per year. Okay, so the COPT for the two tie line interconnection is shown here. Yeah, so it can exist in 3 states. Either both of the tie lines are operating, so this is the probability. You know how to calculate that, right? COPT for 2 lines, it's like using binomial distribution. A plus U square is equal to A square plus 2AU plus U square. So this is A square, this is U square, this is 2AU, yeah, where A and U can be calculated from these numbers, right? Correct? Yeah, so this is what you get anyway. Hopefully you can verify those numbers. So the effects of the tie line constraint is included by combining the capacity outage states of both the equivalent assisting unit from system B and the tie lines. Yeah, so again, the process is the same. You have a different model. This is the model of the tie line now. We can actually get 20 megawatt over from system B. Previously, we were able to transport only 10 megawatt, but now we are able to transfer up to 20 megawatt. So this is the tie line capacity model, but we also have the model from system B. So the system B model has to go through the tie line model, and then you have to get a new model of the tie line constrained capacity outage probability table, correct? So that's what we do next. The tie line constrained equivalent assisting unit model of system B is given in a table, but we'll add it to the table of system A. The new installed capacity in system A now is 95, isn't it? Because we can get 20 megawatt support from B. The loss of load results for a capacity outage greater than 45 megawatt now. It was 35 megawatt before. In the isolated system, it was 25 megawatt, right? With the 10 megawatt line, 35. 20 megawatt line, 45. The modified COPT is also shown for you. The cumulative probability of the first load loss event greater than 45. So that happens to be 50. That will give you the loss of load expectation in system A. Okay? And that turns out to be 0.405290. As expected, the reliability has improved significantly. Previously, it was only 0.30 something. Now it is 0.40. The lower, the better. Correct? So those calculations are shown here. I'm just going to show you this table, and we're going to stop here. So the capacity outage states from equivalent assisting unit, and this is the tie capacity states. So if you go across, these are the states from system B. If you go across, these are the states from system B. If you go in terms of the row, these are the states from the tie line. And I need to put the two together, right? So for example, if the capacity out from system B is 0 and the capacity out from tie line is also 0, then I get this probability. How do I get that probability? How do I get that probability? Yes? Remember, independent events, probability of A and B is probability of A multiplied by probability of B. So you know the capacity out 0 megawatt from system B. You know capacity out 0 megawatt from the tie line. You multiply the two and you will get this probability. Okay? And then you see there are different states. 10 megawatt out, 0 megawatt out from here, but 10 megawatt out from the line. So total will be 10 megawatt out. 10 megawatt out here, 10 megawatt out from the line, total will be 20 megawatt out. So you have different states and you can come up with this capacity outage probability table, passing the available table from system B through the tie line model, yeah, and combining all the common states. So there are more than 2 states with 10 megawatt out. So you see here 10 megawatt out from the system B and 10 megawatt out from the tie line. 10 megawatt out from system B, 10 megawatt out from the tie line. You can only transmit 10 megawatt, is it not? Yeah, because tie line is 20, correct? And then if tie line is 20 megawatt out, you can't transmit anything, correct? So that's why you have to combine some of these states which are similar and then get this particular table. We have done this in a previous example yesterday, so it shouldn't be too hard. Okay, and then we obtain the modified COPT, and then the cumulative probability of 50 or more out is this one, 0.405290. That's the risk in the system, the new risk in the system. Clear? Okay. So compare this value with the original index obtained for 20 megawatt of fully reliable tie capacity. We can see that the inclusion of the tie line availability results in an increase in the risk expected. We are quantifying the increase. We expect that the risk will increase, surely. So such an increase is only marginal since the tie line availability is, unavailability is usually very small. As I mentioned, tie lines are fairly reliable. Okay? So we have seen the impacts of tie line. We have seen the impact of tie line capacity. We have seen the impact of tie line forced outage rates. Now the only thing that I want to talk about is multi-connected systems, and we'll probably complete this tomorrow, okay, in addition to the distribution systems. All right? Thank you very much again. You have a nice day, and